with you,
Sorry.
from my playing with it, it's the ultimate ADHD tool because you can click on it and say, you could take another call or get distracted. Then you can come back to it and say, catch me up, and it'll tell you everything that was said since you left.
Oh, this is the AI tool.
Yeah.
Oh my God. There's too many tools.
Every AI, right?
All right.
OCP was heavily dominated by AI presentations.
Yeah, I guess.
AI is the answer. What's the question?
Yeah. I guess we need to
Answers ready.
All right, guys, let's get going. So yeah, we have a few new members, I believe. So let me just call you out in order. So Jinhua Chen, is this your first time or not? Jinhua, can you hear us?
I think he's having problems with his speaker in his chat box. He's mentioning he's trying to get onto voice.
Okay, Jinhua, no, we can't hear you then in that case. Okay, all right, not to worry. If you get back on, if you manage to get on, you can introduce yourself later. So next, Andrew Downs. Quick introduction for you, Andrew, please.
Absolutely. So it's great to be here with all of you. Am I muted or what just happened?
Something. No, sorry, you carry on. It looks like.
Oh, I see. Okay. So my background is for 5 years, I helped the high performance computing modernization program under the Department of Defense run a lot of their supercomputers. Some of you may be familiar with a system called Excalibur. That was my baby for for most of that duration. And then there was another unclassed system called Centennial that I also helped manage, and then a whole bunch of other ones that I can't talk about. I left sort of my DoD leg of my career to join a series of startups near Texas or in Texas. The first of which was TMG Core, where I was the director of their immersion lab. And then I went on to be a high performance computing subject matter expert for an organization called Silex that focused on healthcare in West Tennessee. And now I'm the vice president of product development at Rosso, working alongside Rick Margerison, who recommended that I join this group. And he talked to me about it and said, these are really your people. Go be with your people. And I said, well, sure, absolutely, why not? So my interest in all of this is just, I've been fascinated with high performance computing through all of its iterations over the decades. I remember sitting there in homeroom in high school, checking on the SGI website, checking on the Cray website, keeping an eye on Supermicro and Tyan, just wanting to see what folks were up to, and just daydream about things that I might one day own or operate. And eventually I got there, and now I'm building those things. So it's just exciting to be closer knit to the community.
Okay, well, welcome aboard, and thank you for the introduction, Andrew.
Hey, Alan, this is Jinhua. Can you guys hear me now?
Yes.
All right. Somehow my laptop doesn't connect me through the voice, and I'm using my iPhone now. All right. Sorry, I need to introduce myself, right?
Yeah, absolutely. Go ahead. Yeah.
Okay. So this is Jinhua Chen. I work for Luxshare. The Luxshare is the interconnect company in China, and we also provide thermal solutions, interconnect and thermal solutions. So Alan, remember we in OCP week, you introduced the whole new concepts. Yeah. Really, I think we can contribute a lot. You can tell by visiting our booth, lots of except the chips and PCBs, the rest of the new concept for the next generation box. I think we have lots of common things we can discuss. My background here today is Luxshare Technologies CTO. My background is high-speed signal integrity. I've been Luxshare for 10 years. Before I joined Luxshare, I was engineering director in TE connectivity to run the high-speed I/O and the high-speed cable groups. And before that, I worked 10 years in EMC as a SI manager, and also SI expert in EMC for 10 years. So my whole life is working on the high-speed interconnect so far. So that's my background. I'm really interested to join this group, see how we can contribute to the industry. Yeah.
Excellent, Jim. Wow, yeah, it was a pleasure to meet you and your team. It was quite surprising. I didn't realize how your breadth of so
Sure, yeah.
your team. And now let's go on to one more. I think we've got Al Ford. Al, would you like to introduce yourself?
Yes. Good morning, Alan. Can you hear me?
Yep, we can hear you.
Excellent. Good morning, everyone. So Al Ford, I am a 25-year career IT person. I'm not a technologist. Sounds like most of you guys. I consider myself more of a talknologist. I'm that purple personality that can help people that aren't as technical understand what the technical people are saying. So that's kind of my role. Last 4 years I spent at Dell Technologies. I was covering artificial intelligence alliances. So I brought all the large companies, NVIDIA, Intel, about 25 of their partners to the federal marketplace initially to help set up skunkworks projects, developing HPC AI labs and capabilities. From there, I joined a company where we were selling data services, specifically helping organizations like Space Force wrangle all their data, get data governance policies, et cetera. So I'm getting further and further closer to the data as my career has moved on. I'm here to better understand the paradigm shift that OCP is offering, and I've seen a lot of Alan's presentations. So wanting to get further into this marketplace and look forward to working with each of you.
Welcome aboard, Al.
Yeah, it's a new word I just learned today, Al, technologist.
Say that again, Matt.
No, it's a new word I just learned today, technologist. I'll just mention.
Technologist, yeah. I've not heard that one before.
Yeah, he's a technologist. Thanks, Al. Welcome.
Yep.
All right. Okay, well, welcome aboard, everybody. Nice to have a few new faces. And I see Jingfu just joined from Inventec. You've been here before, haven't you, Jingfu? Let me just register you in. Okay. Right. So in terms of the topics, the first one was just a quick OCP Global Summit review. So what I'll actually do, 2 seconds. For those of you that weren't there, I gave a presentation, and actually, Bijan, if the actual presentation's gone live now, did I notice yesterday or?
Yeah, they will. They're coming up this week.
This week, okay, perfect. So so those of you that have maybe that seen the wiki, there's an old presentation from 2021 where I went into some of the technical details on one of the early concepts we had. And we took every technical topic and we sort of delved a little bit more detailed. What I did this year round, was really took a step back and tried to give everyone the high level vision and the reason why we're completely re-architecting compute from the ground up, compute architecture from the ground up, with sustainability and energy centric computing in mind. So that presentation only had a little bit of technical detail, but hopefully is a better one for people to get started with if they're coming in cold, because when you see what we're up to, it is pretty radical. But what we also did is I also had the opportunity, the composable memory systems sub-project had a nice little experience center, and they allowed us to have a little 2x2 table, which was tremendous. So I could show off a real physical 3D model of the module, which really helps it's quite surprising. Even showing 3D models is one thing on the computer screen, but having it in your hands, it makes it a lot easier for people to pick up on. And I had good traffic and met a bunch of people, and it was good to explain it. So including the guy that leads the cooling team, Rolf. Was it Rolf Brink? Rolf, I went through the thermal one with him. We've had a lot of thermal help over the years from Boyd in particular, and a few others in Cool IT. So that was good. And he replied in the end after sleeping on it and said, "Oh, I think this is actually fantastic." So we do need to involve more collaboration with these guys in the other groups for sure as we progress this. And we're a little bit off piste compared to what they're doing in their groups. So somehow we'll have to work out how to integrate them more as we go forward. But what I wanted to do was quickly turn my camera on, if I can find it. Yes, here we go. And let me just pull myself full center here so you can see me. I just wanted to show you the module here. I don't know if it works on the TV screen, but you can. Let me turn off my background. Virtual background. None. There we go. Okay. All right. So this is the 3D model. So you can really get a feel of the size of it because it's in my hand. I don't know how well it works compared to actually on the show floor, but we've got the E3.S modules, up to 16 of them in here. You can see the topology interconnect on 4 of them on one side and 4 on the other, giving you a total of 8 topology interconnects here. This is the modules then plugged in. This is a wall. So let me just show you the pieces because that's what I had. I had the fully built one for people to see, and then I had the pieces. It did manage to survive. I think some of the 3D printers are broken, but so this was a piece of the wall of the wall itself. So 1 module's worth, and there was 8 modules high for those people that are familiar with this anyway. But this was showing that the water comes down the wall, cold water in through one of the interconnects, and when we mate it together with everything, it comes into this manifold. Actually, I've got the name manifold. That's a damn good name for it because so this is a manifold where the water comes in one side. On the module, it flows down through all these veins, actually returns across here up to the top in little mini immersions. So this is conductively cooling those E3 modules. And then when we place this is a PCB with the big chip on it. My son kindly made this 3D model for me and painted it nicely. So this proves very, very useful. So we see the big chip on the front, and we see like a mini backplane on the back to carry all these modules. And when that gets that then inserts on there, and we have the conductively cooled element, and then the lid comes on, and the water flows in the bottom part from the manifold here. And then it literally floods. So it's like a little mini immersion chamber here, floods across and then returns back out the top, back into the module here, and out of the return pipe, back on the hot return. So that's a water flow. And also what I didn't touch on is we bring 48-volt power in here on these 2 pins. So that can carry up to 74 amps. So in theory, you could bring 3.5 kilowatts in, I think. But the power comes in here, and in the wall at the moment we're still in the development sort of phase of this, how this wall piece will be going. I'm talking to Murata, the chap he's joined a few times from Murata, basically looking at designing the power brick to go from the 370 volt AC or whatever the infrastructure power is to the 48 volt DC in the wall itself here. And we'll also have a valve control, which is something that we need to design and define to actually control the flow of water. So depending on how much power the module is burning, the outflow is always 65 degrees C out of the module. So we've got reusable hot water for energy recovery purposes. So that's basically the physical module setup, and then we have the E3.S modules that obviously go in here as well. So that proved extremely useful to get people the idea, and we have managed to. I managed to talk to everybody there at the show as well. So a bunch of the interconnect guys, which was very useful, including our new members, and some of the immersion and cooling people, etc. So got a lot of progress. I met Munir there. Munir, I didn't manage to see Tim, unfortunately. I didn't get time to speak to Tim, but we can cover that maybe. I've got a topic on the sideband stuff to go through today. So the event was a tremendous success. I think it was about 4,500 people, the biggest attendance ever. There was certainly a buzz there. It looks like OCP has definitely got to what I would call a tipping point where suddenly the industry is saying, "Hey, this is the way to go." So that was great for the whole OCP community. So that was an update on there. Anyone else want to make any comment on that? Bijan or anyone else? Just a quick overview on the event itself or anything specific?
I'm on mute. Yeah, no, I think you summed it up nicely. I think it was it was our largest event to date. Over, close to 4,500 people came. It was there was a lot of buzz around different areas. There was a lot of work that got done. There was really good sessions. Everything I've heard has been positive from it. So it's been a very positive experience. Yeah, so I think you summed it up quite nicely.
Okay, thank you. All right, so on to our next topic. So HPCM concept to reality. So let me just on our last meeting, which was a month ago now, because we had a skip in the summit, we talked about breaking ourselves down potentially into some work groups. And in terms of getting things moving, the power and cooling, I've got a plan with Progress Analog and the University of Illinois with their conformal coating of copper for cooling purposes, immersion cooling purposes, and they have offered that they can potentially 3D print our manifold, and they have some so that could be quite interesting in terms of the manufacturing of this. We've got several ideas on how to manufacture this, but this is sort of early days. Hopefully we will, like I say, hopefully there's funding coming from a large defense company in Europe, which will help us to sort of put on the gas pedal a bit quicker. We're still working through details on exactly how that will work, but so this one's sort of beginning to take a level of structure, which we really do need to nail down on the power delivery and the cooling infrastructure for sure. Just another one on the power side is one thing that I think it must have been NVIDIA that's done. I thought it was maybe OCP were involved, but it looks like NVIDIA's driven it. There is a common footprint now for these little tiny power bricks that can deliver a couple of phases at 130 amps, and also the two-step going from 48 volts down to 12 and 12 down to these less than 1 volt. So the power density is certainly matured, and there are various power supply vendors of the technology, and that's making the power infrastructure of us building this module to deliver a kilowatt a lot more viable, which is great news. So that's good to see that maturing, and that was on show from several companies in the event, in the OCP event. So that was great. Today, though, I want to focus on the interconnect optimization. I did speak to a bunch of interconnect people, and I just wanted to begin, because we do need to nail that down. So I wanted to start to highlight that. Ideally, what we need to do here is I wanted to socialize what we want to do here, and it would be good to try and set up a little breakout work group. And this is again where, excuse me, Bijan, I wouldn't mind maybe talking to you, because BAPI has done a good job of creating little sub-project work groups. Either they work in a little mini NDA or some CLA. I know OAI is very rigid on a CLA approach to little work groups. But anyway, we need to sort of structure and get it. And I wouldn't mind an interconnect lead to actually lead the work group, rather than me being the spokesperson all the time. And I will certainly attend all these groups for sure. So I want to discuss the interconnect one, and the other one I wanted to start kicking around was the physical part, the Libra BMC hardware, the BMC hardware side of this, the sideband management, etc., of the card, because I think this is quite important. Again, there's lots of good work going on, but we need to consolidate this. We want to make our modules standalone bootable. We don't want to put a full-blown DCSCM security control module on the module for sure, but we want enough logic in there to be like a BMC where it can standalone boot and it can become part of a bigger management system, maybe a DCSCM remotely controlling it.
Hey, Alan, in that vein, there was an interesting contribution for a satellite management controller, which is a subset of the BMC. You should really look into that.
Okay, could you ping me a link on that email? Sure. That would be good. I'll put it in the chat. So you notice as well, I've separated out the BMC and fabric management software, which is what CMS is doing as a separate. But obviously these two do work hand in hand, and again there's complexities here, and I really want to advance the sideband management beyond this I2C world as well, into maybe what we call a control plane network architecture. So that's going to be an interesting discussion group in its own right. So those are the two I wanted to, they're the two biggies that I think I'd like to make some progress on. And so if we can get some sub-project leaders on these two, or work group leaders under this sub-project, then that would be good, where we can maybe make some faster progress outside of this bi-weekly meeting. Okay, so let me just go back into here. So I've got the interconnect requirements discussion is the first one. So again, actually, if I just let me bring my, I've lost the controls. Where have the controls gone? Where did the controls go? Maybe if I stop sharing, they'll come back. There they are. Okay, I've got my camera on still. So just on the interconnect. So there's a couple of things on the interconnect I want to start talking about. We can see that we've basically got a mini backplane here of all these connectors, literally covering the entire back of the card virtually. But on the front, we've got this big processor with 4,000 or more balls on it. We also have the power supply infrastructure that we need to design around. And so these connectors typically have through-hole connections on them for mechanical rigidity purposes. And we can't, and alignment purposes, for pick-and-place alignment purposes. So we can't afford any holes. In fact, holes in boards because of connectors often cause major congestion of routing problems through my experience over the last 30 years. And so we really need to get rid of all of the through-hole interconnect things on these these are standard TA1002 connectors here, and the ones we've shown here are actually MCIO. I'll come on to the topology ones. The topology ones are somewhat more complex in terms of our choices. So we've got a thought process to go through there. My plan is not to answer any of these questions today. It's just to introduce the challenges we need to overcome to make this into a reality. So firstly, we need to get rid of all through-hole interconnects. So let me just, if I just switch back to sharing my screen. Let me bring up my model. So I've just pulled in a couple of connectors here. So this connector here and this piece here are the MCIO connector. I'm not sure which variant this is from which manufacturer, but basically this is the MCIO connector. This is the 8-lane PCIe interconnect. So MCIO is the PCI SIG standard for it. So we can see that obviously our signal pins are all surface mount, but on this one you can see that we've got these mechanical alignment here. I think these are alignment pins here. They're quite big ones on this particular connector. And then you've got some metal ones which are just part of the metal frame, which are mechanical rigidity, because you can very easily tear these connectors off when you've got something the size of an E3. Well, this is actually one of the topology connectors, apologies. So this is one of the edge ones. Actually, let me just pull in a TA102, the E3.S1 as well, just so you can see that. There you go, 4C plus vertical. Let's just bring that one in. Okay, so there's our 4C plus. Let's just pull that up and away. Okay, so we can see this this one has 1, 2, 3, 4, 5 metal tabs on it for mechanical rigidity, and then 2 alignment pips on either end. So they're the through-hole features of the card. These are the ones we need to replace. We can flatten these to be surface mount, fairly decent size surface mount pads to give it some rigidity. Now the fear will be, well, without this rigidity, we're gonna tear our connectors off. But because, if you can see my picture again, because we've got this manifold with the thermal cooling of the individual drives, etc., and any active cables, then this is going to give us very good rigidity of the module, stopping it from the side to side, which would be what would easily tear off the connector. So we're going to have less. We're not going to have as much of an issue with that when we consider the fact that we've got this manifold around those connectors, giving them some level of rigidity. We may need to consider some other some additional features as well, but that's the initial thinking there. And in terms, so actually, you know, let me just cover the basis. So that's the first one. Is we want to get these connectors. Now these are quite easy to remove manually. If you are doing a prototype population, we can take the connectors, but it would be good if the connector manufacturers could maybe consider variants of this with the surface mount only. So I've spoken to the chap who's just joined, Jinhua, and I've spoken to Molex, I've spoken to TE, I've spoken to Samtec. So we need to do that. We'd obviously need to do this in OCP, so that there would need to be a standard that is open, that everyone can adopt, you know, under the OCP rules, because this is a very important area for interconnect plan. Well, actually, that's something we're going to need to discuss, because really it's being able to plug E3 modules in is the important thing. Ideally, it would be good to have the same footprints as well. And then, but the features in the connector, how good they perform is down to the different manufacturers. So that's the first one. So we need to do the TA1002 connectors, the 4C and 4C plus, and we need to do the MCIO. Now, on the MCIO, we do have, yeah, let's stay on the connectors at the moment. So the MCIO, just to remember, is the, where's my board? Is back to the video, is these topology connectors. So the 8 connectors on the outside. So we need to, these are ones where the cables will plug into. And the reality is here is these can take many forms in terms of the signals they carry. So they could be proprietary links like an NV link or an Infinity Fabric or a UPI from Intel, or they could be PCI CXL, as we know that CXL is becoming a fabric. So being able to connect between CXL switches into the CXL-based devices. Obviously, we've got the E3 devices that could be CXL, like the Samsung drives could be directly mated in here. But these cables for the topology will carry that. So we need an MCIO connector gives us the ability to take PCI and CXL between modules. However, if we think about it, the Ethernet is another popular one that we'd want to connect between devices as well, and obviously these proprietary ones. Now, Ethernet doesn't typically carry any sidebands. MCIO has a whole bunch of sidebands, and so we could say, well, you know, what I really want on these connectors is I'd really want one connector for all standards, right? Now, that maybe we need to do 2. One of the main reasons we might have a problem with that is the impedance is like PCI CXL is 85 ohms. Ethernet has been traditionally 100 ohm impedance. Apparently, I heard that they've just gone down to 92 ohms, which was the midpoint. So IEEE with Ethernet did their part of trying to align. It's a shame they didn't come all the way to 85, and then we wouldn't have to move the other ones. But I don't see any time soon any change to CXL and PCIe going from 85 to 92. So we're still a few ohms apart in terms of the nominal impedance of these interconnects. Now now you can buy interconnects sometimes 2 variants of the same connector, which has been optimized for different impedances. So that's a possibility. But the other thing is there is a speed challenge as well. So obviously Ethernet today is at 112 gig and going to 224. And if you don't believe 224, it was shown as being real on the show floor. It looks like NVIDIA have done it. No one would admit it, but if you've ever watched NVIDIA's SIGGRAPH videos of the way their chassis plugs together, you will see the connector vendors were showing that interconnect, and that's apparently 224 gig capable. So so it would be nice if we had one connector that could do the highest speeds possible, and we could cover both PCI, CXL, and Ethernet as a minimum, and hopefully as a result of being able to cover those, we should cover everybody else as well. That's ideally where I'd like to be. Unfortunately, MCIO is not really qualified above. I think even it's only at PCI Gen 5 now, and that they're working on 6. And then there's 7, which is 128 gig. But if you look at other connectors, they're a little bit more proprietary on the Ethernet side of things. Molex have their near stack, and I think Jinshu did show that they also have a license to make the near stack ones as well. And Samtec do have their Accelerate interconnect, which does the Ethernet at the 112. I don't believe that near stack or Accelerate are going to make it to 224 as they are today, but we could possibly normalize on one of these. And then the next question is, MCIO, PCIe carries a tremendous amount of baggage of sidebands, which are expensive for the cable manufacturers to handle these horrible little single-ended signals. In fact, they prefer to make, it's cheaper to make cables with twin-ax than it is with single-endeds often. So what I'd like to do, and I'm coming a little bit onto the sideband side of things, but something that Lattice did in open source to an OCP has adopted is a thing called LTPI, which is basically carrying all of the sideband signals over one differential pair. And so I'm sort of beginning to say, should we as a group define a standard where we can on the connector front, where we've got 8 lanes plus a transmit and a receive sideband, so 2 pairs, 2 diff pairs for that, plus maybe a transmit and a receive clock if that was desirable, and that would be it basically. So a connector that's optimized for that. Strictly speaking, the MCIO could do that for us. And by the way, we also need power, because we want to be able to plug in active cables. Now, PCI SIG did have active cables back in their previous generation. It was called OcuLink, because the O stood for optical and the CU stood for copper, the symbol for copper. But when we had MCIO was brought to the party, they forgot about optical cables, and there's no power on the current MCIO. So we need to bring some power onto the cable so we can do active cable. That's for near package optics and for also active cables, which when we start talking chiplets, there's a lot of interest there that we could do. So that is where we could innovate on our interconnect. And because it's between our modules, it's HPCM to HPCM, then we, you know, arguably we can do that and cover those sidebands with the sideband management circuitry that we have on the card. I said a lot there. Hopefully I've not confused too many people, but so the bottom line is I think we have an opportunity for innovation at the topology connector if we want to go there. We can make that innovation fit into somebody's existing module, like a connector like the Samtec Accelerate or the Molex Near Stack. But we need some of those optimizations, and we want to think about exactly how we go about that. And if we can make it so that we can support PCIe, CXL, and Ethernet from an impedance and a speed perspective. That should allow us to cover all those proprietary ones as needed, like an NV-Link or an Infinity Fabric, etc. So that's one area where I think we can make a significant contribution to the industry in general, actually, for trying to sort this interconnect out, because it's a bit of a myriad of a mess as far as I'm concerned. There's just so many different connectors out there addressing these different things. So that's the area that I wanted to really cover. There is one other area. Let me just stop sharing again and go back to this full screen. Again, on these, so the other thing on this is on these connectors, we have our module that plugs in. And you can see the interconnect there. We have this thermal connection as well. In fact, I talked to a couple of the interconnect guys about this, and I had an idea from, I think, from Chris at TE actually. So we've got like interconnect pins on here. They're like big fat electrical pins, but they're sprung loaded for, or a bit like EMC gaskets was the best way somebody described it to me, where we're trying to get a thermal connection there between the module and the water flowing through this manifold. And so basically, when you plug when you plug one of these modules in, you get that thermal mate of the body to it. Chris had a good suggestion of actually put the EMC gasket equivalent, like the thermal gasket, on the module itself, and that would be a lot easier to assemble. And then as you pushed it in, you would get that thermal connection. And if you were mating, and then for whatever reason you had a mating issue, you could service the gasket, you know, if it was worn out through too many insertions or something from a thermal interconnect perspective. But so I'm thinking that the interconnect guys are going to be the ones that can help us out with this thermal interconnection. It's not electrical at all, it's just thermal. And also another one on these topology cables, if we've got an active cable, if you think active optical cable today is these ginormous QSFP going to OSFP cages. And that's because they're old-fashioned optics, which is a lot more power hungry. And silicon photonics has the promise of getting us down to around a picojoule per bit. I think Ayar Labs is demonstrating a complete link at around about 4.5 picojoules per bit. So at the moment, we need to be able to cool about 5 watts in these little connectors. So by a similar mating assembly, we can actually water cool these active cables. So we can get to tiny optical interconnects for near packaged optics, which I think is an interesting stepping stone to these co-packaged that we want to go to. We've also discussed how we can support co-packaged optics potentially. So again, investigating those options, but we need to get a little bit closer to the silicon photonics guys for that. But we want to get to get these liquid cooled, conduction cooled, should I say, on the cables will give us a lot more opportunity for either active electrical cables with little chiplets. You know, we can talk about a picojoule per bit on one side to talk to the chip that's very nearby, and a picojoule per bit to drive a beautifully clean twin-ax cable, maybe a meter or two. That can be interesting on the electrical front, and we could be in around about 2 or 3 picojoules per bit for the whole buffer inside the cable, or we could go optical and go hundreds of meters. And so that's where I think we've got some tremendous opportunity for innovation there. So that's why interconnect is hopefully I've given a good feeling of why interconnect is such a big topic for us to drive down. I'd like to try and set up. So I'll ping a few people on that I think would be worthy to join. I mean, Jingfu, you're the only interconnect representative on the call today. Sorry, Jinhu. Would you?
Are you talking about me? I'm Jinhua.
Yes. Yes. So
Okay.
Jinhua. Sorry, Jinhua. Sorry, I beg your pardon.
Okay.
Sure.
Uh-huh.
Yeah, if you'd like to, I mean, if you're interested in helping us drive this, then but I'll try and convene a meeting of just the interconnect people. So, and anyone else that'd like to join, Munir, it might be applicable for you to join us as well, just from the from this sideband question of LTPI, etc.
Sure.
Definitely.
All right. I realize I'm only got 10 minutes left here, so let me switch over to the sideband one. So what I wanted to do here, let me just find an old slide that we talked about. Here it is. Yeah. So hopefully you can. Oh, am I sharing the screen? I'm not sharing the screen, am I? Let me share my screen again. Okay, so here is an old diagram. This has been around for well over a year in terms of what we're planning to do on the sideband management. So I see this as being the same basic circuit that we're going to use for all modules, and the connection to the processors or accelerators will be the only variant. But we want to make sure that we can cover the bases, like processors typically have a little 4-lane PCI interface of some sort for controlling, for talking directly to the BMC, plus a bunch of what they call LPC, their low pin count or interface. And so we want this standard BMC that can actually boot the module in standalone. I think that's a very important point. So the structure you see here, but you see this is very tightly intertwined with the interconnect, because the interconnect carries a tremendous amount of baggage. We've got like, I'm not sure exactly yet how many, but something like 8 to 12 pins of sideband on every one of these TA1002 connectors. And what you see there is you see, this is a Lattice ICE 40 device, which is basically a small CPLD stroke FPGA, where we carry the blue lines are basically the sideband signals. Oh, in fact, in the bottom right-hand corner, it says, there you go, you've got 11 IOs, there's 9 GPIOs and 1 I2C bus on those sidebands. So we want to take those into these tiny little ICE 40 devices, and we can then turn them into what they call a single wire sideband aggregator. And that just simplifies routing. Rather than routing all of these many signals across the module, it aggregates them into this single wire, and it doesn't, we can use a lower pin count FPGA in the controller as well. In just talking about the controller in the middle at the moment, so we're used to a couple of big industry, well, not big necessarily, but a couple of industry players that have always made the BMC hardware, the chips, the controllers themselves for many, many years. But in the spirit of openness and security in particular, they've, as well as having the open software like OpenBMC that everyone's adopting now, they also want to have much more of an open hardware. The entire RTL of the BMC wants to be open source, or there's a drive to that. And that's something that's called Libra BMC. And both Lattice and Xilinx, I think DCSCM modules have been built with both Lattice and Xilinx chips in them, running a Libra BMC, taking a Libra BMC approach. So that's what we're doing with this. And so that will have a soft processor in there, I'm guessing, or maybe a hard processor if it's fully open sourced. And basically we will have your entire BMC, any of the low-level RTL doing things like fan management, power supply monitoring, and all of that will also be controlled out of there. Oh, and you see I've got a separate ICE 40 on the power management side of things, but again, we can look at that. But finally, you'll see the 8 topology connectors, the 4 at the top and the 4 at the bottom, and they've got there. I've already shown that they've got the LTPI, the LVDS tunneling protocol interface for carrying. So what we're proposing, or what I'm proposing here, is that on those topology interconnect, we get rid of all these little sidebands. We still have a sideband, but it's just over LTPI on these interconnects. So that's the main argument there. The one piece that's missing from this is that I've been chewing on, and Mitch, who's on the call, and me and he have discussed this on privately and I think on 1 or 2 of these calls, is we could possibly do with a control plane where you're not relying on a cable between 2 modules all the time to get some level of communication, and it only be a sort of a sideband between some host controller and some device at the other end. So I won't bore you with the details there, except to say that one of the areas is because we have modules neighboring each other on the wall, they're literally millimeters apart. we could do a little bit of free space optics communications there at very low cost. If we could get a low cost little LED, we could do like gigabit Ethernet very easily in 4 directions, maybe in 6 directions off these modules is another possibility. And so, but just at in terms of my investigations of free space optical communications, sadly, they're pretty poor on the ground. They're like 1980s 10 megabit per second stuff. When I look at what's coming out of these super smart startups in the silicon photonics, they're all focused on the holy grail of co-packaged optics, when I think there could be a tremendous market for them in short distance free space optics. But there we go. At much higher speeds than what we see today. So I'm wondering whether we could get some innovation there and maybe get a very low cost control plane that could be in the speed range of 10 gigabits per second, you know, or at least between 1 and 10 gigabits per second. And that would go through this Libra BMC is the other area that I would like to pull the thread on. I think we can probably get by with these topology carrying LTPI, certainly initially, and the composable memory systems work group, and there's on the software side with Redfish, etc. They're trying to work out the discovery mechanisms of CXL. You know, where's your memory reside? And so there's a lot of work going on, but I think if we can innovate at this hardware level to make things a little bit more step-in repeatable, and a more sophisticated control plane, trying to put us out of the 1970s and the I2C bus into much more of a sophisticated control plane world, then I think that's a big win for us all. So that's my other topic. So that's a group that's going to have a lot of work to do. Munir, are you happy to be the guinea pig to lead that as you're driving from Lattice side of things?
Sure. I think this will be a great opportunity for us as well. So
Okay.
Yes, we do have the signal aggregation, plus we also have the leadership LTPI. There is few other press releases that are going to send you that we're actually combining Lattice FPGA plus ICE40 and X1 package, but that could be another interesting option for the security perspective. It's going to be a tamper-proof BMC where we're packaging ICE40 holding the keys in a single package with the Lattice, and there's an X2 version coming that will be with an built-in ASICs, built-in SoC in the package together. So I can send you those, press releases.
Okay, no, that'll be good. Yeah, any of your latest innovations. Obviously, this is over a year old now, this diagram. So, and also real estate is obviously a biggie on this module, right? So those ICE40 devices were tiny. And the actual controller itself, obviously, we need to get that in there. So we don't want that to be too huge over.
Yeah, we're targeting about 21 by 21 at this time, which is basically the A speed. But we can look at all the other options. And ICE40 is like what, 2 millimeter by 2 millimeter.
Yeah, the ICE40 is tiny. Yeah, so you can park the ICE40 right next to the connectors. Okay, that will work. I realize we're at the top of the hour. Any quick questions or from anybody? I know that was a lot of information, but I think this is where we need to start stepping up stepping on the pedal a bit more. These are the areas where turning the module into reality needs a bit of energy from the various experts. And again, on the sideband management side, there's a lot of work going on in OCP that we don't want to reinvent the wheel, but I think that we could bring a little bit of singular thinking to this, whereas I think that people are just looking at the way the world is and trying to fit into the way the world is, and instead of driving where the world could be if we start with a clean sheet. And that's what I think this sideband management could be. We could be a nice pioneer for the industry in this one. From a hardware infrastructure perspective. Okay, guys.
Adam, are those slides are online? We can access, or?
Sorry, say that again.
The slides or the pictures you showed to us, Are those are online, so we can access?
This slide deck is called HPC: The Next Generation. You'll see it. It's sort of in a live one. I've not updated it recently, but this is in that slide deck is slide 61. It's sort of a linear progression of various workings. But all of our presentations are recorded. The minutes or whatever few minutes I create, and the transcript is online. Now we'll have an AI summary, which I'm really looking forward to see what that looks like, Bijan, from this call. If there are any slides presented, then we also upload those as well.
Sounds good. Thank you.
All right, so check to the wiki. I try to keep that as up to date as possible. Okay, everyone. Well, thank you very much. Hopefully we can start to make a little bit of progress here. So that's into the real world rather than the concept. So
Good update.
Looking forward to it.
Yep. Thanks, Alan.
Thanks, guys.
Thanks.
Bye.
Thanks, everyone. Great meeting you.
Thanks.
Thanks.
Bye.